The last thing that we do is if the orbital's less than half full, then we minimize the total J value. So here's an example where we have, say, we're looking at the d orbital. So we always write them out like this. We write the 5 levels of the d orbital, and what we're really doing is we're writing m sub z going from -2 to +2 there. And so if we have a configuration of, say, d7, if I've got 7 electrons, I fill it like this. So first I put the first 5 in with all the spins up because I'm trying to maximize spin, but then I've got 2 left over. I've got to flip them, and I put them in the most extreme case I can. You can make it either the most negative or the most positive. It doesn't matter, because what we're doing here is we're trying to get the most m sub z as we can. We're trying to get the most z component that we can. And remember that the largest value of the z component of the angular momentum gives you the angular momentum quantum number as well. So we're using the z value as the way of figuring out what the total angular momentum value is. So we put the last 2 electrons in the d7 into this -2 and -1 orbital, and that lets us know what the L component is. In fact, so now we add everything up, and the only excess ones are the -2 and the -1, so that adds up to -3. Absolute value of that L is 3. Also, there are those 3 up spins that are unpaired. That gives us a 3/2 total spin, again for maximum z component, and that the degeneracy of 3/2 is twice 3/2 is 3 plus 1 is 4, so that's a quartet. And then with L equals 3, that's SPDF. That gives us a quartet F term symbol for this configuration. And there's several things that I'm pointing out that I'm trying to get at here. One is, notice that we're filling d orbitals, but the sum of the orbital angular momentum gives us 3, which is an F term symbol. The capital F is different from the fact that we're in d orbitals. Those are disconnected from each other. So please don't make that mistake. And then we figured out the spin, and we got the quartet. There's another cool thing here, and this has to do with why it's minimum J if it's less than half full, because we left behind 3 holes. And those 3 holes behave exactly like positively charged holes when you're talking about semiconductors and things like that. The absence of the electrons there, you can almost think of them as just 3 holes that are spinning around. And in fact, you get the exact same term symbol. You still get a quartet F if you were to consider those 3 holes only. And so actually a D3 and a D7 orbital are going to have the same term symbol. They're going to be both quartet F. But the D7 is behaving as if instead of having 3 electrons, it's got 3 holes interacting with the nucleus, and those holes have a positive charge, and the nucleus has a positive charge, and so they interact with the magnetic field in the opposite sense. And so rather than wanting to be the minimum amount of J, you want the maximum amount of J if it's more than half full, because you kind of switch over from electrons interacting with the nuclear the magnetic field there to the holes interacting with the magnetic field there. And so you switch the sense of the orientation. So the rule is that your minimum J if you're less than half full, and your maximum J if you're more than half full is going to be the lowest energy case. And you can easily prove to yourself that if you're exactly half full, there's only one J value anyway, so the rule doesn't need to be specified in that case. I want to keep looking at this configuration. So here we are, the same thing. We've got the D7 configuration here. So we have L equals 3, S equals 3/2, G of S is a quartet, so we have a quartet F. And there's the holes that we could think of in this situation. So now the question is, what is the J value? So we have an L of 3, an S of 3/2. So the possible value of J is going to be 3 minus 3/2 is the lowest that we can get, which is 3/2, all the way up to 3 plus 6/2 plus 3/2 is 9/2. So we have 3/2, 5/2, 7/2, and 9/2 are the allowed values of the total angular momentum. So those are the J states that we're going to have, and we're more than half full. We're dealing with holes, And so the lowest J value is going to be the one with the lowest E. So in this case, we go quartet F 3 halves, 5 halves, 7 halves, and 9 halves. Worth pointing out, if we had a D3 configuration, then you would see for the full spin-orbit coupling term symbol, you'd have a quartet 9 halves, 7 halves, 5 halves, and 3 halves. So that's how you can tell them apart if you just see the term symbol. So this one, the lowest energy is quartet F 3 halves. If you had the D3 configuration, that would be quartet F 9 halves as the lowest energy because of the opposite sense of the effective charge in the spin-orbit coupling. So that's our term symbols. We can do the check. G of 3 is 7, G of 3 halves is 4, 7 by 4 is 28 total states that we expect. Now let's go to those J values. G is 4, 6, 8, and 10. We can add them all up, and you get 28. So that does check, and that's the check you should always do. I guarantee that you will be asked that on an exam. So you gotta always do that check, and now you know that the whole thing worked out nicely. Let's look at another case here. Let's do a D10. So there's D10. I've filled the subshell entirely. It's a completed subshell. And the thing to point out here is that whenever I have a complete subshell, now all the spins are anti-aligned with other spins, and so the total spin angular momentum is 0. And also if I just add up -2 plus -1 plus 0 plus 1 plus 2, I get 0. So that the total orbital angular momentum is 0. So whenever I have a complete full subshell, the term symbol for that subshell, and you can always write term symbols for individual subshells, if it's completely full, that's a singlet S. And singlet S just means boring. There's no spin angular momentum, there's no orbital angular momentum, it's totally spherically symmetrical, and it's done. It's not going to do anything with anything. It's just a bunch of electrons in a sphere with no net values of interest. There's a single state, there's a single way that the whole thing sets up, and it's basically, put on a shelf, and you don't really have to worry about it for anything evermore. So that's why we only pay attention to the not completely filled subshells when we are constructing the overall term symbol and worrying about the energy levels. Now, there is, as you well know, there are these special cases where Hund's rules don't quite apply. So we're totally filled subshells. They're always singlet S there. So let's look at the case where we have a 5s2 4d4 versus 5s1 4d5. So this is one of the exceptions to Hund's rules, and in this case that's actually molybdenum, and this is actually an answer to one of the exam questions from last year. So I've got 2 in the 5s, which is lower in energy than the 4d, and then I've got 4 in the 4d orbital. And that would be how I would fill it according to Hund's rules, sequentially. But as you well know, in reality, one of those 5s electrons instead is flipped and sort of promoted into the 4d to give us a 5s1 4d5 configuration. And at this point, another thing's worth noting, and that is we can write the term symbols for individual orbitals, and when they're not completed, then they won't be singlet S. And then what we can do is we can find the total spin and total orbital angular momentum for each of the subshells, and then we add each of those in turn together to get the overall interaction. Let's say that this one plays out fairly simply because we're only dealing with an S here. So the 5s2, that's a singlet S. That's filled, and like other filled subshells, it's not very interesting. 4d4, just the black electrons there to the left. 4 electrons with 4 halves, or 2 total spin angular momentum. 2 times 2 plus 1 is 5. And so we have a quintet, and our total orbital angular momentum there is, let's see, I've got 4, so I have 1, 2, plus 1 is 3, and a 0 is 0, and then an opposite 1, I go back down to 2. So I have only an orbital angular momentum, total orbital angular momentum of 2 SPD. That's a D. So we have a quintet D is the term symbol for the 4D4 subshell itself. We never do J's until we've got everything done. So no J values yet. We'll get there, but no J values yet. Now let's look at the 5S1 4D5 configuration. Excuse me, yeah. Now we take those and we add them together. We combine the singlet S and the quintet D, and the singlet S is a singlet S. It does nothing, and so the overall term symbol, without the J values yet for this electronic state of the atom of molybdenum, is going to be a quintet D. Now let's look at the 5S1 4D5. The 5S1 is a doublet S, and the 4D5 is now a sextet S. It's an S because we've half filled the subshell, so all of the orbital values have a negative m sub z going with the m sub z that's positive to counteract them. So there's no orbital angular momentum, but now there's 5 spins in that d orbital, and so the degeneracy is 6, and we have a sextet S there. So the doublet S and the sextet S, there's always going to be S. The total orbital angular momentum can't ever move away from 0, but we can have the doublet and the sextet, the spin of a half and the spin of 5 halves, can either add together, giving us a septet S, a 7S, or they can subtract off of each other and we get the 5, the quintet S. So there are 3 possible term symbols for molybdenum at the lowest the lowest set of states, and that's what the first 3 term symbols were what an exam question asked for. And the next question is, what are the possible J values here? So the quintet D, we've got a J, we've got the S. The spin there was, let's see, what was it again? The total spin was 2, and the orbital angular momentum was 2. And so now we can go all the way from 2 minus 2 is 0 to 2 plus 2 is 4, and we're less than half full, so 0 starts it. So we go the quintet D 0, 1, 2, 3, and 4 are the spin orbit states in that order. Then we have whenever we have a value of 0 for either spin or orbital angular momentum, there's only going to be one J value. So we have a septet S, and the septet S has got to be 3, and then the quintet S has got to be 2, because that just specifies the J. Remember, we put J in the subscript there. So the spin and the total angular momentum are the same thing, but we use the degeneracy in the superscript for the spin degeneracy, and we use the actual value of J in the subscript. So we have septet S3 and quintet S2. So that's the full set of spin orbit levels associated with the first 3 terms. We've got the quintet D 0, 1, 2, 3, 4, septet S3, and quintet S2. So finally, the question is, well, which state is which? Who wins and what order do they come in? And since this is an exception, you won't be surprised that the septet S3 is the grand winner. So promoting the electron from the 5s2 to the 5s145 gives us the lowest energy. But the higher spin also wins. So we take the higher spin because that once again gives us the greatest anti-symmetry in the spatial exchange wave function for all these electrons. And so the septet S3 is the lowest energy case. And in fact, if we look this thing up in NIST for molybdenum, we find the septet S3 is the ground state. The quintet S2 has an energy 10,768 wave numbers above that, and then the quintet D states come here, going from 10,966 up by steps of a couple hundred wave numbers, 11,140, 11,450, 11,800 11,860, and 12,346 finally for the quintet D4. And this is kind of interesting, right? Because now we learn a little bit about what's going on here. It's not just the difference in the antisymmetry of the exchange wave function that makes for the exception to Hund's rules, because the quintet S2 is actually still lower in energy than the quintet D states, right? So not by much at all, but it does win out. So even there where it doesn't get that extra boost from the extra spatial antisymmetry, it still is the number 2, the first excited state of molybdenum. But there is a lot of energy to be had, right? So there's 10,000 wave numbers associated with 11,000 wave numbers almost associated with just getting that extra antisymmetry in the spatial exchange wave function for those electrons. So that's a big deal. I mean, 10,000 wave numbers is a third of a bond, and so that's a lot of energy there, and that's why we care about that. And then, if we look at the quintet D levels, those guys are separated by a couple of hundred wave numbers only, about 400 wave numbers really. Remember, 200 wave numbers is kT, is a typical amount of energy at 300 degrees Kelvin, and so those levels are all within sort of thermal, or they're just sort of on the edge of being reasonably easy to get at thermally one to the next. So the difference in energy matters, but they're kind of all in play if you're up there. And so that gives you a sense of what, having the spin and the orbits aligned or not, how well that does, the spin-orbit coupling terms there. We're getting 400 wave numbers or something out of it. And again, compared to thermal energy, compared to 200 wave numbers being RT or KT, that matters. It matters a whole lot, but it's not as big as the differences that we see in the actual energy levels. It's basically a happenstance that the quintet S and the quintet Ds are so very, very close to each other. But we see that the spatial exchange antisymmetry is a big deal, and it's certainly got a whole lot to do with that exception to Hund's rules. But then there's also an element that comes into play just from basically where those things are in space, and the fact that the electrons are farther away from each other, and lots of other things going on. There's a whole complicated array of different phenomena that have to do with that exception to Hund's rules.